If we now look at what the computer does, so we're going to start looking at data types, and we'll start with the integer and binary numbers. Now, in the previous part of the lecture, I mentioned this thing with Boolean data, and that computers love Boolean data. We have zeros and ones. Well, this is why. Computers are just a collection of switches, essentially on or off the whole time. And those switches are collected into a number of switches that sit together, and we call them a byte. And as it is, by convention nowadays, for the last sort of 40, 50 years, we've had 8 bits in a byte. So a bit is one switch, we can say, on or off, and we collect all those, a number of bits, and we turn them into a byte. Now, this number, this 8, that we have 8 bits there, it's a convention that arose in the late 50s, early 60s, and isn't necessary. There's not really anything that says it has to be 8 bits. It's kind of a sort of minimum level for what was useful for the applications at the time when computers were being developed. Initially, there were quite often 6 bits. That wasn't quite enough. And why this was important was simply because of the cost. At the time, just adding one more switch, which means you have to add on one more switch in lots of different places, it became very expensive. You can watch a film on this on Computer File if you like. But the byte is our basic block of data the computer wants to use. And we can add bytes, we can have multiple bytes added together, so we can have 2 bytes or 4 bytes and so on. But the fundamental structure is this 8-bit in a byte structure. What does this do? Well, it's based on binary numbers, where numbers are represented by zeros and ones, and we have these 8 switches sitting together. We take them as a collection, as one number, one word, and if we have all of them are turned off, then it's a 0. That's kind of logical. If the right-hand switch is turned on, well, that represents a 1 in that column there. This first column, this first number of switches represents a 1, and so we get a 1. To represent a 2, well, we can, as each column can only be on or off, and 0 was, off was 0, on was 1, we've used up all of our possibilities there, so now we need another column. And in the same way as when we count from 0 to 10, we've filled up, when we get to 9, we've filled up all of our possibilities, and so we need to utilize another column. When we say here, the next column, well, that's full, so this, and we want to add some information, so that must mean it's a 2. If that's empty now, and that one's full, because we've filled that previously, we've added 1 more, and so now that's equal to 2. So 1, 0 will be 2. In actual fact, in the entire, all 8 bits, the byte, what it is 0, 0, 0, 0, 0, 0, 1, 0. That becomes a 2. And then if we add 1 more to that, well, we put it in, there's space for it here, because that was off. So we could turn it on, that one's turned on, so we've got 2 plus 1 is 3. And if we continue all the way along, we can fill that up to a maximum of 255. So if we add up all of these, so this column represents 128, that column represents 64, that column represents 32. If we add up all of those columns, the sum is 255, which is important, and that number comes up all the time. So remember it. It's a very important number when working with computers. 0 to 255, these are the values that we can store natively, as it were, within 1 byte. And this will turn up. You will see it regularly. 0 to 255. And another thing we can look at here, just out of interest, when we have a 1 in this right-hand column, the numbers are odd. When we have a 0, it's either a 0 or an even number. 0 is considered by many to be even as well. So this is just a little quality we have of the data here. But what's happening over here with our signed integers? Well, we need some way of saying it's a negative number. So how do we do that? Well, in the same way that we know that if the 1 on the right-hand side, if it exists, we have an odd number. Well, if we put a 1 on the left-hand side, it's a negative number. This is a convention. It doesn't have to be this way, but this is the way it's being implemented in computers. Generally speaking, for a signed integer, what we have is 8 bits in a byte, and if the left-hand digit is a 1, then it's a negative number. If it's a 0, it's a positive number. Now, but because we've used this space, because we've taken this up to represent whether it's a positive or a negative number, we don't have 128. We don't have this column for storing the number 128. That's gone, which means that we can only get to between minus 127 and plus 127, because the sum of these is 127. 127 plus 128 is 255, but we don't have the 128 there. We just have this to say whether it's positive or negative. So here we can see that 1, 1, 1, 1, 1, 1, yeah, and so on. That was 255. But here, the same series of switches all set to on, we're saying equals minus 127. And again, that's just an instruction we set to the computer that when you see this binary number, it means this. It's the same, they look exactly the same, but we've instructed the computer that this is the case. This is a negative number. This is how computers work. This is the basics of the computer. So this is our integer. And we can add multiple bytes together. If we were to add on another byte, so instead of just being 8 bits, we've got 16 bits, we can store an even bigger number, because now we're adding on the next step up. We're adding on the 256 column here, and then more and more and more, so we can get much larger numbers. They expand very rapidly, our storage capabilities, as soon as we add on another byte. So that's how we are storing numbers. The integer storage number works on the computer. But as we can see, as we add on all these bytes, the numbers, they do become much, much larger. But we need to ask ourselves, do we need all of this storage? So if we have 64 bits of storage, we can store massive, huge numbers. That's great, but if our data it doesn't even come close to this, why use all of that? Because you're having to feed all of those bits into the processor for every single pixel or every single data point, every piece of storage data stored. You have to use all of these bits. If you define the data type for your data as being this, it will use it for everything and take up far more space than is actually needed. So if your data only goes up to 65,000, you don't need more than 16 bits. Don't even bother with 32. It's an unnecessary usage of the space. So look at your data, find out what you actually need, and that's how you can store it. And this is a simple matter, and it may feel irrelevant in the modern world when we can have terabytes of data storage on our computer. But in terms of processing and doing something with that data, this is where it becomes important. That movement from the hard disk to the processor, that's where things can really slow down. And then another data type that we're probably all more familiar with is text. So how does a computer store text? It's a system of switches on or off, so it's stored as numbers. It's stored as the same thing that we were looking at before, as those integers that we were looking at before. But instead of those numbers, as we saw in that example, we could say that 1 byte, that was all the ones were filled, so it was 8 ones in a row, that could either represent 255 or minus 127. And it was just what we told the computer that meant. That was the difference. We can even tell the computer it's not a number at all, it's actually a letter. So we can take those numbers and say this is a particular letter. And that instruction to say a number is actually a letter is what we call ASCII or UTF-8 or any one of a number of different schemes. We don't need as many schemes as there are out there, but there are. But UTF-8 is now the most common. ASCII was for a long time the most dominant way of encoding text. UTF-8 has taken over and is now the most common, and this has got more than enough characters for almost all cases you're going to come across. You're not going to be short of characters when using different types of characters when using UTF-8. But it also contains other commands. For historical purposes, there are commands for such things as carried return, like on a typewriter when it went moved around, or the delete button. That's also encoded in there, as well as I pointed out previously, text versions of numbers. So when we look, we have our binary numbers here. I've broken them up into 4 bits, like 4 bits above 4 bits, but that's 1 byte all across there. So the instruction for delete is 011111111, which is equal to 127 if we were to translate it into a number. But instead of translating it into a number, we're translating it into an ASCII command, which is delete, or an ASCII character, delete. So we would erase something if we were to program that in. And that can happen. Accidentally text disappears without you understanding why. Very rarely, but it can. But also we can just take numbers like the number 65, which is represented in binary, or this binary number, which might represent 65, if we choose to have it represent 65, can also represent the capital A, and so on and so forth. So we can represent characters and instructions in the ASCII or UTF format using these binary numbers. So I've just translated these into normal numbers, as it were, decimal numbers, so that we can understand them, just to quickly get an overview of what that number is. But actually, when it comes to ASCII, what we mean is that is that. That is that, not that. So as you can see here, 1 is a 49. Why 1 isn't 1 is a good question. Would have been more convenient in many respects, but it isn't. Live with it. There's nothing we can do about it, and it doesn't really matter for us. The computer's doing all the heavy lifting here, so we don't have to worry about it too much. It's just the way it is being stored. But the important point here is that all of this is needed to store the character, to store the letter. So when we want to write a word, we need multiple bytes in order to write the word 1 or the word 2. Or, for example, here, when we think about writing out text, GIS is fun. So I've color-coded these. So this, this byte here is the capital G, this byte is the capital I, this byte is the capital S, but then we have a space, and that needs to be coded as well. So we need to code for space, and then we have the I and the S, another space, and the F and the U and the N. So that long string, all of that, for the computer, is the text GIS is fun. So if we want to represent the number 255 as numbers, this is even not writing out TWOFIVE, but 255 in ASCII, for example, it becomes all of this. Alternatively, if you just want to write the number 255 in binary as an integer, it's just these 8 ones here. So we could replace all of that with that. It becomes a third as large. Again, so this is thinking about how do you really want to store your data? And this is a very trivial example, obviously, but already we've managed to save a lot of space by storing it like this. Again, it's not the hard disk, generally speaking, that's the problem. It's moving things from the hard disk to the processor so that you can do something with the information. That's where these problems occur. And another concept, one more thing to get in place, is the idea of no data, which is kind of similar to a NaN, not a number. They're not exactly the same thing. Not a number. Quite often they're used interchangeably. Sometimes there's not a better alternative. But the not a number just means that your calculation perhaps didn't work out right. It may have gone to infinity. Sometimes some languages, systems have a character for a way of storing infinity, a representation of infinity, and a negative infinity as well. Others don't, and you just end up, or perhaps you try to divide something by 0, and it will just say this is not a number. It's it's not correct. Or it is some text. It's not a number. It literally means not a number. Something's gone wrong. I can't work it out. But we also have more in GIS perhaps than in other things, the concept of no data. And no data isn't quite the same. As I said, sometimes it's used for the same purpose, to say the calculation didn't work out, or there's something else here that's not quite right. But no data actually should really be interpreted as, I don't want to say anything here. There might be data somewhere, but in this file, this part, this area, wherever we are, no data. I'm not saying anything. I am not making a statement one way or the other about this particular place. It's no data. It's not incorrect. It may not even be unknown. It's just right now within this file, I'm not saying anything. And that's what no data really actually should mean. But as I said, it quite often gets used to represent other things, such as, oh, there's an error, or you divide it by 0, or it's infinite, or something like that. So this is the no data as opposed to NaN. But no data is, generally speaking, what you will more often come across in GIS and GIT. And then one last type of data that we want to talk about here in this section is metadata. Metadata is data about data. And what is metadata? What is at least as important as the data? And in fact, in some ways, more important. Yeah, that's tricky. But I would say that data, as it says down there, data, without metadata, data is just numbers and words. It doesn't mean anything. You don't know what it is. And this was a real problem once upon a time within remote sensing and GIS, that you could receive a file from a good source, from a government source or a government agency, that was nothing more than the data file. You had no idea, there was nothing in the file associated with it to tell you what it was. Which coordinate system were the data in? What were the numbers representing? Is this a near-infrared data file, or is it just a normal color image, or what is it? All of that could be missing, and you had to work it out for yourself. You'd hope that the person you'd received the file from had told you, or it was what you had actually asked for when you applied to get the data. But it wasn't necessarily so that you would be informed of this. You just had to make that assumption. Nowadays, things are a lot better. Generally speaking, all data is provided with some form, some degree of metadata. Not always everything that you might want, but at least you know how the data is to be interpreted. What's the type and the scale? What are we talking about here? These things that we've gone through before. And when was this data collected? Is this still relevant for me? What time of year was it? How many years ago was this taken? How good is it? What's the spatial resolution of the data? What's the temporal resolution? All of these questions. And without answers to these, with the data that you have, with the numbers, as it were, then you almost have nothing. But if you have good metadata, in some respects, you can even do some analysis just on the metadata. Is this a relevant file? Do I need it? No. Is this something that I can, or yes, can I move it forward in my processing? Does this exist so that I can do things? So you can do some sort of meta processing just on the metadata, which can be an advantage. It means that you can exclude or include data before analysis without having to run through it and find out that it was worthless or very good. So metadata is essential and important, and you will probably in your working lives, especially if you have to go back to historical data, and when I say historical, it might only be from 20, 30 years ago. I'm not talking about going back to dark ages. You might find data, a file of something that could potentially be useful, but there is no description of it, and you will have to guess. And that's when things start getting tricky, and really it's something you want to avoid. Nowadays, everything should have metadata, and things that you create, the things that you do, will need metadata. And this is something that we will be working with a lot. You need to inform other people of what it is that you have. Otherwise, you have nothing.